Right, so this is the continuation of the notes for 1.2. So you're looking at continuity, and to determine if a function is continuous, the basic way to describe that is you're able to draw the graph without lifting your pencil point up. So this graph I could go through. Don't leave. So you can draw that first graph without lifting your pencil point up. If you have something like this second or this third one, you have one point that's missing from the graph there. In this one, it's redefined up here. In this one, it just doesn't have that point. So I can't draw either one of those graphs without having to lift my pencil point up in order to go from that hole on to the next part. And then the last two here, you have actually a jump in the graph. There's a big space in there, so you'd probably draw this part first and then jump up here and do that. You had to lift your pencil point. And same with the last one, you have an asymptote here. So you can't get from this bottom piece to this top piece without lifting your pencil point. So this is sort of the basic definition of continuity. There's a much more formalized definition which involves the concept of limits, which is going to be the last thing that we cover in pre-calculus. It's the beginning of the calculus part. And we'll go through. The notation for limit is this LIM. And then it says x approaches some value, whatever this a value happens to be. And then inside here is just your function. So what that looks like is it's saying, what is the height of the graph coming in from the left-hand side? So if you look at this graph here, coming in from the left side of that point A, the height for the graph looks like it's getting close to 0. Coming in from the right-hand side of the graph here, the height at A is up here, which, I don't know, maybe +1, some positive number there. So coming from the left side, coming from the right side, they don't have the same height. So that function is not continuous, it's discontinuous. Same with this one. Coming from the left side, the graph's going to negative infinity. Coming from the right side, the graph's going to positive infinity. So it's not continuous. And then this last piece of it, f of x equals f of a, that's this piece of it. Instead of this point being up here, it would have to be right here in the graph and plug that hole up there. So the height and the limit from the left and the right have to be the same. But we'll get into that in more detail as the course continues on. So no worries about that quite yet. All right, so let's find asymptotes. I know I'm doing this with the eraser here. So asymptotes, there's actually 3 kinds of asymptotes, and then another situation which is holes. So we'll look at 2 of the 3 asymptotes in this section. So vertical asymptotes, and you've seen these in Algebra 2. This refers to the boundedness of the graph. Where is the graph headed? So vertical asymptotes is your values get closer and closer to a particular x value. Where is the graph headed? So if you look at this graph here, as I get close to -1 or +2, one side of the graph is headed to negative infinity, the other side is headed to positive infinity. So these are vertical asymptotes, and I'll abbreviate VA for vertical asymptotes. Vertical asymptotes are always in the form x equals, occurs at x values, so x equals -1 and x equals +2. If I plug x equals -1 or +2 in whatever this function is, I'm always going to get an undefined value. And then part B says this is the function right here that you're looking at. And if you look at this, where I can get -1 and +2 is if this denominator is equal to 0, I would have undefined values. So if you take x squared minus x minus 2 and set that equal to 0, you're going to get x equals -1 and x equals +2. So those are the 2 values that cause the graph to be undefined. Those are the vertical asymptotes. To find vertical asymptotes, set the denominator equal to 0, see what x values you come up with. Before you find vertical asymptotes, you should find holes. And holes in the graph, we had a picture in the beginning part of the notes with that. A hole is just when a factor ends up canceling out, numerator and denominator. So you need to find these first. Before you find your vertical asymptote. So the first thing you do with the problem, you're going to look at it, you're going to factor, cancel out any common factors. That'll be the holes. And then you'll look at what's left to find vertical asymptotes. And we'll put this all together in just a second. And then the last piece is horizontal asymptotes. And horizontal asymptotes is talking about horizontal asymptotes to the tails. So if you're talking about a horizontal asymptote, it doesn't really matter what happens close to the x-axis there, the y-axis, the origin part. Horizontal asymptotes are talking about the tails of the graph. So what's happening at the ends of the graph here? So as this continues on, what is those tails actually headed towards? Are they headed, the height headed to negative infinity, positive infinity? Well, the height here is getting closer and closer to 0 for both of those. So that's what it's referring to is the tails of the graph. What's the height that the tails of the graph are getting close to? So in this case, your horizontal asymptotes, and they're always in the form y equals, in this case it would be 0. So horizontal asymptotes, what are the tails of the graph? What are the heights of the tails of the graph getting close to? And then there's a shortcut to find horizontal asymptotes. Not like the way it's written in the notes here, but I'll give you my way here. So we said for this one, this is the equation for this graph that we're looking at right up here. So instead of this, I find the highest power of x in the problem. And then we want the ratio of its coefficients. So if you look at this problem here, my horizontal asymptotes would be at, well, the highest power for x in this problem is right here. It's x squared. So I would say to myself, how many x squareds do I see in the top? Well, you don't see any x squareds in the top. There are 0 of those x squareds in the top. And then how many x squareds do you see in the bottom? I'm looking at the ratio of the coefficients here. I'm looking at that coefficient out in front, which is a 1. And 0 divided by 1 is 0. And that's your horizontal asymptote. And that's what we looked at back here in this graph here. All right, so let's do a bunch of these where you have to find these asymptotes here. So this will kind of all make sense for you. So if you look at the first one, this is a good example of why you need to factor. So if you factor this function first, you'll see that the x plus 1's cancel, which is a hole in the graph. If you set x plus 1 equal to 0, you'll get x equals negative 1. So when x is negative 1, you're going to have a hole in the graph. The function that's left is this 1 over x minus 1. So this is what we'll refer to now. To find vertical asymptotes, take what's left in the denominator and set that equal to 0. And solve. You may not need to write this out. You might do this right in your head there. So x equals 1. If x is 1, that denominator is going to equal 0 to give you an asymptote. And then finally, horizontal asymptotes, they're in the form y equals. You can use the simplified version of this, like we said right here, or you can go back to the original. It doesn't matter. It's going to give you the same outcome either way. If you look at the simplified version, the highest power for x is x to the first. There it is in the denominator. I don't have any x's in the top. I have one of those x to the first in the bottom, and 0 divided by 1 is 0. If you didn't look at that one, if you looked back at the original function, highest power for x is x squared. I have 0 x squareds in the top. I have 1 x squared in the bottom. Still gives me y equals 0. Right, if you look at the middle one, it doesn't factor, so there's no holes in this graph. Nothing cancels. Vertical asymptotes, I would set what's left in the denominator equal to 0. X is 3/2, so I have a vertical asymptote at x equals 3/2. And then horizontal asymptote. Highest power for x is x to the first. And I actually, for this one, I have an x to the first in the top, I have an x to the first in the bottom. I have 2 of those x's in the top, I have 4 of those x's in the bottom, which is 1/2. So horizontal asymptote at 1/2. And then finally for part C, doesn't factor again, so there's no poles. Vertical asymptotes, if I set this denominator equal to 0, I'll get x equals -1. Then horizontal asymptotes are looking for the highest power of x, which is x squared. Here it is. I have one of those x squareds in the top. I don't have any x squareds in the bottom. So 1 divided by 0, that's undefined, which means there's no horizontal asymptotes for this one. Right? And actually, that problem is going to have the third type of asymptote that we have, which we haven't learned yet. It's coming up. That's going to be the cliffhanger for you. All right, last little piece, increasing and decreasing functions. When you're looking at intervals, you can decide if the function's increasing or decreasing. Increasing, decreasing is referring to the y values. What are the y values doing? Are the y values going up, which would be increasing, are they going down, or are they staying the same? The interval part, what's the interval where that happens? This is talking about the x values. So increasing, decreasing, constant, that's the y values. We want to know what are the x values where that occurs. So if you look at this first one here, our graph is, for always read a graph from left to right, just like a book. So this graph starts here at -5, and then the graph is decreasing. It's going down. The y values are getting smaller and smaller and smaller. Here it's 3, here the y value is 2, here it's 1. So it's decreasing from -5 until I get to x is -2. And the intervals are always going to be in parentheses because technically at -2 the graph is no longer increasing, it's no longer decreasing. That's a turning point. And then if you look at your graph right in between here, it's not going up. The y values are not going up, they're not going down, they're staying constant. And that happens when x goes from -2 to +2. And again, I use parentheses because technically at -2 and +2, it's not doing anything. And then finally from 2 up to 5, the y values are getting bigger and bigger and bigger, so the graph is increasing in that interval. So that's what you're looking at for these increasing and decreasing. Let's try this one. Here's -2. So following the graph from left to right, the graph is y values are getting smaller. So the graph is decreasing from -infinity to x is -2. And then the graph turns around. Now the y values are getting bigger. So it's increasing from -2 to infinity. And it's not constant anywhere. And again, -2, that's the turning point where it changes from decreasing to increasing. And then let's see. These look like asymptotes here at -1 and +1. So if we come up with increasing, decreasing from left to right, the graph is going up. So we're increasing from -infinity till we get to -1. Then I have the asymptote, so nothing's happening at -1. And then my graph is increasing again until I get to 0. So from -1 to, oops, that's a 0. My graph is increasing. And then it's decreasing from 0 to 1, not including 1. And then from 1 to infinity. And I can't include this 1 because there's an asymptote there at that point. And if you think about it, this is the last little piece on the notes. It says, how does increasing and decreasing help you determine maxes and mins? Look at the parabola one. The graph is decreasing, and then at this point is where it turns around and increases. And if you looked at that graph, you could tell me that that point is a minimum. So the graph changed from decreasing to increasing gave us a minimum. If you look at this point right here, the graph is increasing then decreasing. So if the graph changes from increasing to decreasing, I have a maximum point there. And we'll look at that in terms of derivatives when we get to the calculus part. So that's it. So you have some homework problems to go through and do in your book or from the textbook online there.